Hello everyone, today we'll talk about the solution to the problem maximum average pass ratio. This is yet another staircase problem. We've had many of those over the last few weeks. And as I always say, the thing that you should think about when you see a staircase problem is either binary search on the answer or using a priority queue using a heap. I will show here a heap solution. The binary search solutions are typically more general because this extra students variable, the number of iterations, the number of extra students that we have to assign, this is manageable for us to loop over all of those extra students and assign them one by one. If we cannot assign them by one, then typically the heap solution doesn't work, and instead we have to use binary search on the answer. So there are, I guess, some tricky things both for binary search on the answer and for heap in this problem. For binary search, I guess the only issue is that we will be returning a float. So we have this precision 10 to the negative 5. And so instead of binary searching on integers where you know when to stop, you stop when you have only one integer, here you have to decide when to stop. Because at every step you'll be getting closer and closer to the perfect value, but the perfect value is a float. And you have to decide based on this 10 to the negative 5 when to stop iterating further. And for a heap, the tricky part is that we have to always identify the best class to make a change in. And we might think at the beginning that, of course, the worst class is the class that has this division of pass by total, that this division is the worst, right? The class that has the worst current score, let's say, is the class that we want to add a new student into. But this is in fact not correct. We want to optimize the average pass ratio, which is exactly the same as optimizing the sum of pass ratios. And so what we want to be doing is, instead of choosing the class which has the worst pass ratio, we want to choose the class that gains the most pass ratio after adding a new student. So we want to make a step that increases our total score and so our average score the most. And we can just calculate that difference, because that difference is just passing plus 1 divided by total plus 1 minus passing divided by total. You see here that I have the order swapped, so I essentially have a negative sign in front of it. That's because we're using a priority queue. Priority queues are min priority queues, so you want to hold negative values within them because we want to get the biggest and not the smallest value. The biggest gain, not the smallest gain. And the solution is simple if we know that. Calculating the gain is, of course, just a simple helper function. The priority queue will hold triples of negative score and the two values that are necessary to calculate the final score. And you want to use them at the end to calculate the final score, because this is sum of p divided by t. We don't care about this gain here, only p and t, divided by the number of classes. So we start with the priority queue, we put every class in the priority queue and we heapify them. We typically should do it like this instead of heap pushing everything separately. Heap pushing everything separately is n log n. Creating a simple list and then heapifying it is O of n. And now for our iterations. For every student, we assign them to the class that gets the biggest gain. We don't care about this negative gain here, only t and p. So we increase t, increase p, calculate the new triple and push it back into the priority queue. Now I haven't proven that indeed this value of gain is optimal, so this is left as an exercise to the watcher. If you prefer to solve this problem without having to prove that the greedy works, if the greedy is a bit non-obvious, then of course remember there are other approaches, there is binary search possible. You do what you want.